So welcome everyone to this week LIP seminar. So today we have the pleasure of having with us Andy Mastbaum from the Rutgers University. Andy did his PhD at the University of Pennsylvania and then Granger postdoctoral fellowship at the University of Chicago. He joined the faculty at Rutgers University in 2019. Currently is working on several liquid argon TPC-based neutrino experiment, MicroBooNE, they will present the result today, SBN and BooNE. Is interested are fundamental neutrino properties and novel techniques for expanding the reach of detectors. So please, Andy, go ahead. We are really really looking forward for your results.
Wonderful. Yes, thank you. Thanks so much for the introduction and for the invitation. Actually, it's good to be back at LIP, if only virtually. I actually have a photo here of me visiting Lisbon as a student for a Snow Plus meeting. This was actually my first time setting foot in Europe was in Lisbon, and I just can't imagine a better introduction. It's many fond memories of a very warm welcome. So hopefully I can be back in person before too long. So great to be here. So as you heard, I'm Andy Mastbaum from Rutgers University, and today I'll be talking about some recent results from the MicroBooNE experiment. I, just for lack of time, won't be able to get into the full details, but I've included a lot of references in the slides where you can find more information. So before we start talking about MicroBooNE and our measurements with a neutrino beam, I thought I would just set the stage first so that we're all on the same page as far as the standard model and three neutrino oscillations. So in the standard model, we have three lepton flavors, the charged leptons with their corresponding neutrinos, electron, muon, and tau type. We know now that these neutrinos are massive. They have a small but non-zero mass, and these so-called flavor eigenstates of the weak interaction, the electron, muon, and tau flavors, are not the same as the mass eigenstates of the free particle Hamiltonian, but instead are related through some mixing through this unitary mixing matrix, the PMNS matrix U. And this leads to the interesting phenomenology of neutrino oscillations, where in a simplified two neutrino picture relative to our universe's three neutrinos, we get this interesting phenomenology like this, where you create a neutrino in a particular flavor and then go to detect it some time or distance later. And maybe you measure it in the initial flavor, maybe it's something else in a way where the probability depends on a few parameters. So there's this overall amplitude characterized in terms of a mixing angle theta that sets the amplitude. And then this oscillating term that sets the wavelength of these so-called oscillations. It depends on delta m squared, the mass difference between these neutrino mass eigenstates, L, the distance or baseline, and E nu, the neutrino energy. So the idea is you devise an experiment where you control to some extent the initial flavor, the distance, and the energy, measure these oscillations in order to define the constants of nature that are the mass splittings and the mixing angles theta. So this has been the experimental program over the last few decades, measuring all of these parameters of this three neutrino mixing model, where we take our three neutrinos with mixing and measure the mass splittings, where there are now two of them, one around 10 to the minus 3 eV squared, one around 10 to the minus 5 eV squared, and all these mixing angles through a variety of beautiful experiments, some of which I show here, in order to be able to predict what we would expect to see for any particular situation. So thanks to the success of this program, we now have precise percent level measurements of the mixing angles and all of these parameters theta. So an almost complete model that all fits together, with the notable exception of this complex phase delta, which if not 0 or pi would imply CP violation in the neutrino sector, differences in neutrino antineutrino oscillations. And that will be the subject of the upcoming future program in DUNE and HyperK. We're already seeing some hints now of possible values for this delta. So that is kind of one open question remaining in the kind of context of the standard model as far as neutrinos. It's actually one of several open questions that are very interesting. Despite the successes of this experimental program, there's still a lot we don't know. Right, so we have this question of the CP violation. Perhaps neutrino antineutrino differences are related to the matter antimatter asymmetry that we see in our universe. It's a very deep question. We know, for example, the differences in the masses, but not exactly how they're ordered. That's just a kind of experimental question to be answered. We have questions, then about the absolute mass scale of the neutrino. Why is it so small? Perhaps that's standard model physics, or perhaps the smallness of the neutrino mass through some seesaw mechanism is trying to tell us about some very heavy mass scales. And so we have kind of both standard model questions and BSM questions that can be probed with neutrino experiments. In particular, we can actually get a lot of these with neutrino oscillation experiments at either long or short baselines. In any case, important questions and really needing a new level of precision and new detectors to probe. So I'll focus in today on some interesting anomalies that we see that may be trying to tell us something about beyond the standard model physics. Kind of motivated by this question of whether there could be more to the story in the neutrino sector, perhaps additional neutrinos beyond the three types that we know about. So as I say, who ordered that? So I'll give just a little bit of the historical motivation for this and some of the background with these anomalies, the two best known and most significant from a statistical standpoint. So first, we have the LS&D experiment, the liquid scintillator neutrino detector. This was operated at Los Alamos in the 90s. This experiment was looking at stop muon decays in a liquid scintillator detector, looking for electron antineutrinos through inverse beta decay. And what was observed in LS&D, the backgrounds, the kind of expected rate of anti-nu-E interactions are in this seasonal red and green histogram here. The data points are in black. So this is about a 3.8 sigma excess over the expectation. And what's shown in blue is a fit, assuming that we have nu mu bars oscillating into nu-E bars over this very short distance of about 30 meters. So if you interpret this as oscillations, you can fit out the amplitude and the wavelength of this, and this would imply a very small probability, about 0.26%, but a very large mass splitting, about 1 eV squared. So several orders of magnitude larger than the two that I just mentioned that have been measured by all these experiments, the delta m squared 3.2 and 2.1. So that's interesting. It doesn't quite fit with our standard 3 neutrino picture as we currently know it. So as a follow-up to that, the MiniBooNE experiment was built at Fermilab, operating starting in around 2002, and kept this ratio L over E the same by increasing both, looking at accelerator-produced nu mu's and nu mu bars for potential oscillations into nu-E's and nu-E bars. Using a mineral oil Cherenkov detector, I'll show you what some of these final states look like there. Muons in a sharp ring, electrons and photons, electromagnetic interactions look like a fuzzy ring, protons are below threshold, and so on. So MiniBooNE's observations, quite interesting and intriguing. The data points shown in black here, compared with the background expectations with the systematic uncertainty shown in the error bars, is not consistent with the background expectation, and in particular is kind of peaked up here toward very low energies. So this has been known as the quote unquote low energy excess. It's about a 4.7 sigma excess when you combine nu-E's and nu-E bars. It actually turns out to be consistent with the LS&D results when interpreted in the same hypothesis. So quite an interesting finding. So with this idea with oscillations, has been widely discussed and gives rise to this idea and maybe motivates this idea of so-called sterile neutrinos. We know that there's only 3 types of neutrinos that are coupled to the weak interaction, but we could add additional non-interacting neutrinos that we observe indirectly through their mixing with the active flavors, so-called sterile neutrinos. We could add one that's heavier in the so-called 3+1 model. We could add more in the 3+n model. But essentially, we take our nominal spectrum of neutrinos and then add in at a very high, relatively high mass scale, an additional mass eigenstate corresponding to our new sterile neutrino. And then that would mix and could induce these short baseline NUI appearance. So if you take such a model and compare that, so this appearance probability shown on this black curve, and compare that to LSND and MiniBooNE in the data points, that actually provides a pretty reasonable description of that data. So this was very exciting, possible evidence for these sterile neutrinos. But it seems like follow-up measurements and combining other results seem to indicate that maybe the story is more complicated than that. So we have this NUI appearance channel, new Mu's converting into or appearing as new E's. This is showing LSND's measurements as a closed contour here. But if you take this kind of minimal 3+1 model, this would also imply that you have in a muon neutrino beam disappearance of muon neutrinos, and that's been looked for in accelerator-based long baseline experiments. And so far, no such deficit has been seen in the new Mu's. So we have lots of exclusion curves, but no kind of positive measurement in that channel. And so if you combine all this data together, you end up with a pretty small still allowed region for this minimal 3+1 model. So I think it's safe to say at least that there is significant tension among these related channels. I'll mention briefly at the end a dedicated program where we're going after what's left of the allowed parameter space, so we can make a definitive statement about that. In any case, this tension and other kind of BSM motivations have given rise to a much broader array of possible new physics scenarios that could either be probed at accelerator-based neutrino experiments and potentially explain, provide alternative explanations of the MiniBooNE anomaly, perhaps new dark sector interactions producing highly boosted decays that look like a single electromagnetic shower in MiniBooNE, things of that nature. And so if we're going to understand this puzzle, we really need to kind of take a broad look, not constrain ourselves to just this sterile neutrino picture, but consider also other potential explanations. So as a first step toward that, let's take a closer look at MiniBooNE and the results from MiniBooNE and try to kind of unpack that a little bit. So I show here again that same plot from MiniBooNE with a breakdown of the backgrounds. And if we kind of look into these a little bit, these ones that are shown kind of in green are actually due to electron neutrino interactions. So these are so-called intrinsic electron neutrinos, and this is the same topology as the signal, which in the case of, say, sterile neutrinos would be new E's appearing. So what this looks like is like this. So in some interaction, charge current interaction, where we have our charged lepton in the final state, in this case an electron, with the proton below the Cherenkov threshold, and the detector appears just as a single electromagnetic shower. So if you look at some of these other backgrounds, like this one in red that also notably peaks at low energies, this is from misidentification of neutral pion decays. So in some cases, say we resonantly produce delta baryon that decays into a neutral pion and a neutral current interaction. So we don't have the charged lepton to tag it. And in some cases, that pion will decay into two photons that are highly collinear and maybe appear in the detector as a single electromagnetic shower, confusing us with the signal. So these actually are quite well constrained in MiniBooNE with the data by measuring the pinots that do not so conspire to fake the signal. That's actually tightly constrained. And as a final category here, kind of in the tan, delta to n gamma. So this is a quite interesting one. We'll talk more about later. But this is a different decay mode for a resonantly produced delta. So here we have a neutral current interaction producing a delta that's going to decay radiatively. So it's a small branching fraction, a fraction of a percent branching fraction to decay into some unseen nucleon in a single photon, right, which looks just like your signal, a single electromagnetic shower. This one is kind of indirectly constrained in MiniBooNE by using pinots and the branching ratio with some theory calculations, but not directly measured. So in order to kind of understand, perhaps the excess is, due to new E interactions. Maybe that's related to sterile neutrinos. Maybe that's something else. Maybe it's due to photons perhaps from one of these background channels or something else. Maybe it's something else entirely, like some dark sector scalar decaying into boosted E plus E minus pairs. But to be able to answer this question, we're going to need improved event topology information beyond what we get from here, right? And so that is kind of why we have chosen to adopt a different detector technology, the liquid argon time projection chamber. It's kind of a next generation detector type for neutrino experiments, where we get a few benefits. So we have now detailed 3D imaging of neutrino interactions at the millimeter spatial scales, calorimetric reconstruction of energies, of energy deposited in the detector, and very importantly for this particular search, the ability to discriminate between electrons and photons with a few different handles using vertex displacement and calorimetry using the charge deposited per unit distance. So before I get into that, maybe just a quick sketch of how these detectors work. So I have a cartoon here at the bottom of a liquid argon TPC. So this is a big tank of liquefied argon. We have our neutral neutrino coming in this way, interacting with a nucleus, argon-40 nucleus or an electron in the detector, and producing some spray of charged particles in the final state. So as these go through the argon, they're going to ionize it. That immediately will create some scintillation light on kind of nanosecond timescales that we detect with an array of photon detectors that I don't show here. That gives us a precise timestamp for when this charge was deposited. And then all these freed electrons, these ionization electrons, will drift over toward a wall in a very strong electric field, about 500 volts per centimeter, and many of LArTPCs, MicroBooNE is 273 volts per centimeter. In any case, we drift these over toward this wall, which is instrumented with this fine pitch, kind of 3 millimeter pitch planes of charge-sensitive wires. That charge will either induce or induce a charge or be collected on those wires, in either case creating an electrical pulse that we then digitize. And we have these 3 planes oriented at different angles, and by combining our waveforms from those 3 planes with this timestamp from the scintillation light, we can achieve a full 3-dimensional reconstruction of all the charge deposited inside of this volume. That gives us these kind of beautiful and fun to interpret event displays. This is showing one of those planes, a kind of top-down view where the vertical axis is time and the horizontal axis is wire number corresponding to position, where you can really see the power of these detectors. So most likely here we had a muon neutrino coming in from the left, undergoing a charge current interaction to produce this long straight muon track. Also this highly ionizing short proton track. And then detached, it's a little hard to see, but detached from that vertex, we have these 2 showers, which are most likely photons detached from this vertex and coming from the decay of a neutral pion produced in this interaction. So this is a candidate event for a nu mu charge current neutral pion production. Really showing you kind of all the different things we can see in these interactions. On the topic of these photons, so as I mentioned, we have good power to discriminate between electrons and photons. We have a few ways to do that that I show here. So in the case that we require there be something else at that vertex, say we also produce a proton, then we know where that neutrino interaction occurred, and we can tell whether that shower that we see from that electromagnetic activity is attached to the vertex. So if we produce an electron in a charge current interaction, it will immediately start ionizing the argon, and we see this attached shower. And in the case of a photon, we'll have some distance before it will pair produce. So there's a gap between the vertex and the shower start point. But even if we don't require any extra activity at the vertex, we have just a lone shower, we actually still have a handle to tell us apart, because an electron, when it starts ionizing the medium, will deposit energy and look like a single minimally ionizing particle, and deposit about 2 MeV per centimeter in liquid argon, as opposed to a photon that at the relevant energies here is almost guaranteed to pair produce. So we'll generate an E plus E minus pair that will travel along together collinearly, and each deposit MIPS worth of energy. So we'll see double the energy deposition along that track. So I show that in the bottom plot here, which shows both electrons and photons together. Electrons look like a single minimally ionizing particle, this peak here, and photons look like two. So if you draw a cut in the middle, you can do a quite good job discriminating between electrons and photons, even in the absence of any extra vertex activity. So in fact, we combine these two handles to do very, very well on separating them. Okay, so I've argued for how useful LArTPCs can be for such searches. Now let's focus in on the rest of our experimental setup at Fermilab in the booster neutrino beam. So here I show like the bird's eye view of this, where we produce using Fermilab's booster accelerator 8 GeV protons that are then fired into a beryllium target. We then focus the resulting charged mesons using an electromagnetic focusing system and let them decay, producing a beam of almost entirely muon flavor neutrinos, nu mu's and nu mu bars, with about a 0.5% contribution of electron neutrinos. So quite pure, but not entirely pure nu mu beam with a peak energy around 800 MeV. MiniBooNE sits right here, and if you take the sterile neutrino interpretation of MiniBooNE, that would imply about a 0.15% appearance of nu e's coming from nu mu oscillations, and so that's the small excess sitting on top of this relatively larger intrinsic background. Okay, so that was kind of the MiniBooNE era. The future program, kind of the current and future, will be to fully instrument this beamline with an array of liquid argon TPCs, including a near detector, the SBND, the short baseline near detector, which is under construction now, Icarus as a far detector, which is kind of finalizing a commissioning phase now, in order to do a joint search probing these potential oscillations at multiple baselines and multiple detectors, to really have great sensitivity to the sterile neutrino hypothesis. So I'll come back to that very briefly at the end. But leading the way on this, the first LArTPC to operate in this beamline is the MicroBooNE experiment. And so that is what we will focus on today, MicroBooNE's measurements as a single detector. So MicroBooNE is, as I mentioned, a liquid argon TPC. It's about 85 tons of instrumented liquid argon mass. Here's the TPC before installation, about 2.5 by 2 by 10 meters, about the size of a bus. And MicroBooNE started operation in 2015, and we just recently shut it down into a kind of dormant mode just a few months ago after some final R&D. So MicroBooNE kind of leading the charge on this program. The idea is, of course, have this more capable detector right across the street, literally from MiniBooNE in the same beamline. So in addition to making first measurements of neutrino-argon interactions and kind of developing the technology, the main question that MicroBooNE is after is addressing this question of what did MiniBooNE see using these extra handles that we get from liquid argon TPCs. While we're looking at the beam, just a note about that. So this plot just shows our exposure collected over time relative to our close to the total for analysis. And the analysis that I will show is focused on this first 3 runs here, corresponding to around 2016 to 2018. So the rest is being analyzed as we speak, but the analyses that I'll show are about half the statistics that we have on disk. So to the extent that everything I will show will be statistics limited, we have another factor of 2 waiting to be analyzed. All right, so turning more toward the analysis then. So just to kind of set the stage for the ingredients for such an analysis. So these measurements are all single detector measurements, so we don't have the benefit of a near detector or far detector to play against each other. And so the key to probing this low energy excess is to use high statistics event samples, events that we have lots of, to constrain intrinsic backgrounds, and signal channels where we have lower statistics. We'll see examples of that throughout. But for example, if we're looking for an electron-like excess, we're looking for this, the small excess on top of, a small excess of nu-E-like interactions sitting on top of this relatively large component of this 0.5% intrinsic to the beam. And so it's, of course, crucial that we constrain the shape and normalization of this intrinsic component if we're going to try to look for anything extra, sitting on top of that. So that's kind of the name of the game, and that those kinds of correlations come in a few different places that I'll describe in a little bit more detail. The predictions for the flux, the ways that we detect these final states and that they appear in the detector, and the neutrino interactions, the neutrino nucleus interactions themselves that are producing these. So we can use, in all cases, correlations between large statistic samples coming from muon neutrino interactions to constrain the signal topology, say, nu-E interactions. And I'll show how that works. All right, so first, the flux, just a few words about that. So again, we're sitting in the Fermilab booster neutrino beam, where our neutrinos come from 8 GeV protons on a beryllium target. This is mainly nu-Mus and nu-E bars shown here, with a small 0.5% contribution from nu-Es. But where we can win here in terms of correlations is that I show here kind of a schematic of how these particles get produced. And as it happens, the nu-Es that are intrinsic to the beam, the bulk of that contribution is actually coming from the same decay chain as what produces the nu-Mus that we see with very high statistics, constituting 99% of the beam. So that's coming from pion decays to muons, subsequently to electron neutrinos. So the idea is to make a high statistics precise measurement of nu-Mus, and we know all of these branching ratios very well. And so by measuring the nu-Mus, we measure also the flux of the nu-Es. So our modeling for this is based on the state of the art from MiniBooNE. We have a full particle trajectory tracking simulation of our beamline in JOT4, where we use external data measurements for the production of mesons and those initial proton interactions, and then the subsequent rescatters of particles traversing the beamline, so that we can propagate the uncertainties in both production and re-interaction cross sections for all these things. And that model, that prediction and uncertainties gives us about a 12% uncertainty on the integral flux that you'll see on our cross-section measurements. But as mentioned, also introduces very strong correlations between nu-Mus and nu-Es. I show that here in this correlation matrix, showing correlations between nu-E energy bins, nu-Mu energy bins, and these off-diagonal blocks are the ones we're most interested in, the strong correlations between nu-Es and nu-Mus. So that's again the idea. We measure with very high statistics, very good position in the nu-Mus, and that gives us a tight constraint on the flux for the nu-Es. All right. Next, just a word about the detector modeling. So we've put in quite a bit of effort on developing this as a collaboration with, and this is now being used much more widely in the community. But we've put together, in support of these analyses, the most detailed model of particle propagation, electron drift, detector response, and photon propagation that's been done for such detectors to date. Building a state-of-the-art data-driven modeling of liquid argon TPC response, which has given us improvements in efficiency and particle ID and a huge reduction in our detector-related systematic uncertainties. So I'll just briefly sketch some of that with some pictures here. So to illustrate some of that at work, I have here what the raw data looks like. So just waveforms on wires. You can see this kind of ridge structure that's coming from noise contributions. And we see kind of just the ghost of a track here. That's actually getting lost because of induction effects from neighboring wires leading to destructive interference. So we can actually lose a signal that way. So we have both hardware and software noise filtering that helps to clean that up. But then the major thing is to use a full two-dimensional simulation of electron trajectories as they make their way through our wire planes in order to build essentially the convolution kernel for what we expect the response of this full wire system to be, so that we can reverse that to deconvolve the signals that we see in order to more accurately measure the amount of charge that either passed by or was collected on a particular wire. So by using this 2D deconvolution signal response model, we're actually able to recover many details of the event, including this track that got lost and you can barely see with the naked eye, to vastly improve our ability to cluster and reconstruct everything in the final state. Okay, and yeah, this is summarized in these GIST articles here. So there's still many things that happen in these LArTPCs. This is a big bulk detector medium. So we have things like electric field distortions, loss of charge as it drifts through the argon, and so on. So without getting into the full details, we essentially need to calibrate the detector. So we have many ways of doing that, including an in situ laser calibration system where we generate straight tracks using a laser. And we also make very heavy use of, our detector is sitting on Earth's surface. We have a huge rate of cosmic ray muons, and we use them to produce a nice sample of minimally ionizing tracks in order to map out, say, the detector response so that we can calibrate and make sure that it's flat across space. So all of these calibrations are summarized in these references I have here. And of course, at the end of this, nothing is perfect. And in fact, there's many kind of subtle and correlated effects still in this detector response model that we want to capture, and we don't necessarily want to assume that we know all of the sources of uncertainty. So we've actually developed a new way of propagating the residual systematic uncertainties for this detector technology, where we look kind of down all the way back to the wire waveform level, so like the single energy depositions on a wire. We look at data Monte Carlo differences between our simulation and our actual data, using some control samples as a function of various, say, drift distance, other detector variables, and use these differences to characterize corrections and model the residual systematic uncertainties. So that's what's shown here. We actually have a publication about that submitted to EPJC. It's on the archive now. So this new response model has, together with the updates to the simulation, has dropped our detector-related uncertainties from dominant at about 40% to down to about 10%. So they're on par with Flux, and now subdominant to statistical uncertainties. So we're very excited about this, and it also gives us about an order of magnitude better computational efficiency, which is always good. Okay, so a final ingredient here, and one that's particularly interesting for these searches, is the modeling of neutrino interactions. So we're in this very, I guess, interesting regime for neutrino cross sections. So I show the energy range here for MicroBooNE in this gray band, together with kind of the world's neutrino cross section data, including 1 point on Argon here at much higher energies from Argonute, and very little data here down toward 200 MeV, where that low energy excess signal would appear. So we're looking for potential new physics in a region where we actually have quite poor a priori constraints. And so it's really up to us to ensure that the models are doing a good job and include the appropriate degrees of freedom for capturing the uncertainties in this region. So in recent times, there's been intense theoretical development that we have taken advantage of for these analyses, and in particular, inclusion of many kind of nuclear physics effects. As we get toward lower and lower energies here, the nuclear physics impact on the cross section becomes more and more important as we're kind of moving from probing single nucleons to probing the nucleus as a whole. So just one illustration of that, which could be a seminar unto itself. I show here a muon neutrino charge current scatter with not a single nucleon, but this correlated nucleon pair, which produces this final state with two proton ejection in the final state, a so-called two particle, two hole interaction, which really, this kind of interaction wasn't appreciated until after looking at MiniBooNE data, and only recently has actually been integrated into neutrino generator models. But including diagrams like this can actually lead to a large enhancement in the cross-section for particular regions of the energy and momentum transfer space. Shown here, it's a 50% enhancement here. And meanwhile, other effects like this so-called RPA suppression, this has to do with medium polarization, modifying the effective electroweak couplings, can lead to equally large suppressions of the cross-section in different regions of the kinematic space. And of course, the measurements that we make integrate across all of this. And so, where your particular flux and interactions lie, could have a quite large impact on the event rate that you measure. So just showing that kind of in our own data, this is from a MicroBooNE measurement. We have these two particle two-hole interactions that add to the cross-section for very forward low energy transfer muon scatters, and these RPA effects that are tending to suppress quasielastic interactions, and they're competing in this most forward bin, right? So it's important to understand all this and make sure that you're attributing, any data Monte Carlo differences to the right physics when we project that then into our signal channels. At any rate, to make sure that we have, fully captured this to the best of our current knowledge, we pioneered, working closely with the Genie collaboration, the use of the latest version of Genie version 3, which includes all this for the first time, this latest theory-driven modeling. And comparing these updated theory models to world data, we found that we actually saw some discrepancies comparing not tuning on our own data, but comparing to data from T2K with a very similar flux. That the models weren't doing a great job out of the box reproducing that. So we've actually performed our own tuning of these models in Genie to T2K CC0 pi data in order to take into account the existing measurements at our energies that we already have available. And we've also developed newly, which will be included in the next release of Genie, the corresponding uncertainties for all of these degrees of freedom, which are constrained for the first time by these fits to the world data. You could read about this in a paper we've recently submitted to PRD. Okay, so putting all this to use and showing that our modeling is doing a good job, I won't get into the details, but we have a quite extensive cross-section measurement program. So we've measured for the first time many important channels for neutrino argon interactions of these energies. This started with in 2019 with a first measurement of the double differential cross-section for nu mu CC inclusive scattering on argon, where we actually saw some evidence for the suppressions of very low energy transfer interactions as predicted by including these new nuclear effects. So that was some motivation to move to these updated models. We actually just recently submitted to PRL and kind of follow on to this analysis looking at energy dependent cross sections in the CC inclusive channel is actually taking advantage of the latest modeling updates. So dramatically reduce systematic uncertainties and measuring in terms of things like the energy transfer from the neutrino to the nucleus. So really a much more direct probe of some of these nuclear effects than we've been able to do before. We've also measured pi naught production. This is important both as a background to electromagnetic shower searches and as a tool for developing our EM shower reconstruction. Here we find actually pretty good agreement with the models. And we've also turned to some more exclusive or semi-inclusive cross-section channels, measuring quasielastic-like interactions with one muon and one proton in the final state, plus some additional kinematic cuts to get upwards of 80% purity in quasielastic interactions. That's what's shown here. Again, pretty great agreement, except for very forward-going muons, further evidence for these extra nuclear effects, and a measurement of CC nu mu's with at least one proton, but no pions in the final state, a channel of great relevance to neutrino oscillation measurements, where we see a consistent story in these muon angles, but very importantly, show kind of a new frontier in our ability to push down proton momentum thresholds and really understand what's happening in proton kinematics, particularly as we move toward low momentum on account of our very low tracking thresholds, thanks to this very fine-grained spatial resolution. So this was all new news. We've also measured electron neutrinos, not using the booster, which is where we're looking for its possible apparent signal, but using a different beam. We actually see, we sit off axis from Fermilab's other neutrino beam, the NUMI beam, neutrinos from the main injector, which has a lower overall flux being off axis, but we have it has a relatively larger fraction of NUEs, about 5% NUE contribution. And we have measured both a flux integrated cross section. Here you can see a neutrino coming from the wrong way, B and B straight across, and NUMI being off axis down that way. So a flux integrated cross section measurement, and most recently submitted to PRL a differential measurement here, where you can actually see this is relative to our tuned Gini model, actually doing a quite good job describing NUE interactions. Okay, so altogether, we like this slide because you can't read the tiny print here, but as you can see, we've been very busy with building the groundwork for these searches. Just in the last few years, at an ever increasing rate, publishing over 40 papers covering low-level detector modeling, analysis techniques, neutrino cross-sections, a handful of DSM searches culminating in these first low-energy excess results. This is accompanied by over 60 technical notes. We always make sure that we document what we're doing, and all of our conference talks are always accompanied by at least a technical note for further documentation. So with that, let us then turn to the topic du jour, addressing the MiniBooNE excess, where I'll spend the balance of my time. So we can ask with MicroBooNE's data a few interesting questions, right? Whether MicroBooNE is compatible with background expectations, whether we are compatible with the short baseline neutrino oscillation hypothesis, maybe with, say, the LS&D or MiniBooNE best fit. But the specific question that we answer in this first round of results is whether we are compatible with the excess, the MiniBooNE excess. Where what I mean by that is we can take the MiniBooNE data excess, shown here, background subtracted, and make an assumption of what model produced that. So let's say this is produced by an enhancement, some energy-dependent enhancement in the rate of electron neutrinos. Perhaps those intrinsic to the beam or from any particular source. So we take the MiniBooNE result and the MiniBooNE Monte Carlo together with our particular hypothesis and unfold that into a what the enhancement looks like in terms of a neutrino energy spectrum, shown here. And then that gives us something that we can plug into the MicroBooNE simulation, letting the simulation take care of the cross-section differences between carbon and argon and all that, and ask, given what this looks like in MicroBooNE, how compatible are we with that, right? And that gives us, the other hypothesis now for a two-hypothesis test that we perform. So we can do that, for any such hypothesis. So I show here an enhancement of NUEs that could also be an enhancement of a photon-like signal, like neutral current single photon production, or insert your interpretation here. So we focused on these two, as I'll show. So all of the analyses that we do follow the same basic structure. We have multiple analyses that I'll talk about. In all cases, we do a blind analysis. It's a staged blind analysis. So we develop analyses on Monte Carlo and a small open data set. So we have 3% open data and additional larger samples that are filtered to ensure that they remain signal blind. And then we divide our selections into kind of our so-called far and near sidebands, where we're able to step toward our signal box, moving toward lower energy, where we expect the excess to be larger, and more signal-like in terms of PID parameters. And importantly, so all these analyses are of course reviewed and get frozen prior to proceeding with any of this unblinding. So what you see are the results from analyses based on a very small amount of data and the Monte Carlo. So we take that, we then apply that to a much larger exposure, about 6.8 times 10 to the 20 protons on target, out of our total, which is about double that. And so we'll of course repeat these on the full data set. So in all cases, so we have actually multiple complementary reconstruction techniques probing different final states, both electron-like and photon-like. And I'll give some motivation for why these. So we search for a photon-like excess in one channel and 3 different possible electron-like signatures. In all cases, the strategy is similar to this. We have our kind of signal sample that has various backgrounds. So we use high statistics samples, say muon neutrinos, along with some auxiliary samples that constrain particular backgrounds, and then do a simultaneous joint fit. So we essentially use the data with this model that I described with systematics to in situ constrain the backgrounds to the signal using the data itself. All right, so first, let's talk through this single photon search. So the idea here, coming back to this MiniBooNE picture, is we have this resonantly produced delta 1232 baryon that decays radiatively with this very small branching ratio, which looks signal-like in MiniBooNE. In LArTPC, if you require a proton, again, you can look for the shower displacement, or if you don't require a proton, you can still tell if this is an electron or photon using energy of the calorimetry information. So this is a kind of a particularly interesting channel because this has never been directly measured in neutrino scattering. The current best limit on the production of this mode comes from T2K, this publication here, and it's about 100 times the standard model prediction. This is a perfectly good standard model process. Just so far, we don't have the sensitivity to measure it. What makes this maybe a particularly intriguing case is it turns out if you turn up this tan background by a flat factor of about 3, that provides a really nice fit to this excess. So if we do this signal unfolding, it turns out this is on average a 3.18% enhancement flat in energy. So you could explain this by just cranking up the effective branching ratio or the effective cross section for this process by a factor of 3 relative to these limits that are currently 100 times the standard model. So the way this analysis operates is by separating the signal into 2 different topologies. So a single photon either accompanied by a proton or not. So I show those in a cartoon here. 1 photon, 0 protons, 1 photon with 1 proton. And this signal selection proceeds using a set of boosted decision trees that are trained for isolating particular types of backgrounds. So there's 5 boosted decision trees for the 1 proton case where you have some extra variables, 3 BDTs for the 0 proton case. And in either case, the dominant background for these is neutral current pinon decays, where say you lose one of the photon showers goes outside the detector, and you're left with just a single shower, maybe the proton. So what we do is we also measure those by looking at these other topologies, 2 gammas with 1 proton, 2 gammas with no proton, shown here. And we directly measure these. That is what is shown here in these plots, along with an actual data candidate, teeny tiny proton and a displaced shower. And then these get fit simultaneously with the signals to provide an in situ data-driven constraint for the pinots that are shown in pink for these 2 channels here. And you can see, the data Monte Carlo agreement is not perfect here. There's a little bit of a normalization difference. And so by doing the simultaneous fit, that essentially becomes a correction to the backgrounds. So without further ado, here's what that looks like, the results of the single photon search for the 1 gamma 1 proton and 1 gamma 0 proton. Again, dominated by these NC pinot backgrounds. And what we would expect for the MiniBooNE excess under this hypothesis is in this dashed yellow line here. And what we see is entirely consistent with the background, maybe even a little bit low. So these measurements actually disfavor the hypothesis that the MiniBooNE excess is due solely to such an enhancement in the delta to n gamma channel at about the 95% confidence level. And having seen nothing here, we can actually set a 50 times improved upper limit on the effective branching ratio for this mode, and that is shown here. in the this upper limit, this exclusion in the pink, relative to the standard model prediction. So actually, we'll get close to that with the full data. So this analysis has also been submitted to PRL here. Okay. So I see I'm short on time, so I'll try to get through this quickly. But moving on then to the electron-like search. So the model here is that we have an energy-dependent enhancement in the electron-neutrino rate. I showed you this plot before. And to look at this, we actually use 3 complementary search channels with different kinematics and different reconstruction techniques. So first we have a charge current quasielastic-like channel where we make a selection to really isolate QE-like interactions, which has nice, clean, easy to reconstruct 2-body kinematics at the expense of some efficiency. We have a CC0 pion selection, which is interesting because it's very close to the MiniBooNE topology, where you would reject any pions in the final state. This selection also does not make use of any event kinematics, so it's semi-inclusive in that sense. And then finally, a CC NUI inclusive search, which is very high efficiency and also being fully inclusive, doesn't care about the hadronic final state, and so has relatively little dependence on the hadronic modeling, in addition to being very high statistics. So all kind of getting at different questions, right? So we have this very clean topology, we have this very MiniBooNE-like topology, and then we have this fully inclusive strict test of this hypothesis that this is an overall enhancement to the NUI rate. Okay, so again, in MiniBooNE, this looks like a fuzzy ring, and in LArTPC, this looks like maybe some hadronic final state with an attached electromagnetic shower. So first, this the CCQVlike channel is based on a deep learning approach to reconstruction, showing here this raw data and then a semantic segmentation network labeling quite accurately these proton stub as track-like pixels and this shower as shower-like pixels. This then goes on to higher and higher levels of particle ID. So we do such a selection for both 1 electron, 1 proton samples and 1 muon, 1 proton samples. Apply some additional kinematic cuts to get it to about 75% purity in quasi-elastics. So you actually have pretty great energy resolution here. It's about 15% resolution on the neutrino energy. But the focus here is really on the dominant, this very clean channel for NUI interactions. We make the simultaneous measurement of the new mu's, that's what's shown here, in very good agreement with our tuned to external data model. And this provides a constraint on both the flux and cross-section models in a joint fit. And the PRD, yeah, the archive link here is submitted to PRD. Okay, so next then we have our 0 pion selection using the Pandora reconstruction we found in this reference here. Again, MiniBooNE-like, again, using a series of BDTs. Here we break the selection into 2 channels with no protons and any number of protons greater than 0. And again, select both nu mu and NUI selections to fit them together for a constraint. So here I show nu mu's compared to data, an example of the BDT separating out our signal topology. And for this analysis, we've also used data from NUMI, this other beam, to provide a data-driven validation of the NUI selection, shown here in good agreement with the data. Finally, we have our inclusive selection using a different still reconstruction technique that's using a tomographic combination of our 2-dimensional wire plane views. This is called wire cell, and described in these references. This is a very high efficiency selection. We see all the NUIs and operates using a 7-sample fit where we use separate samples of fully contained and partially contained NUIs, nu mu's, and pi naughts from charge current interactions. And the 7th one is a measurement of neutral current pi naught production. So here again, showing the muon neutrino selection, which is used as a constraint. Also submitted to PRD. So bringing it all together, this is what we see when we open the box and look at the signal samples of the NUIs for the QE-like, inclusive, and then these 2 different topologies with no pions, with protons or without. And the prediction for the MiniBooNE excess is shown in all cases in this dashed red. So you can see across the board, pretty much we're seeing something that's consistent with background or below. So actually all of these measurements together disfavor this electron-like low energy excess as the sole hypothesis for the MiniBooNE anomaly. A different way to see this is just doing combining all these spectra as a counting analysis. Here shown for the single photon, and here for an electron-like low energy excess, where we have rates that are in agreement with or below the predictions, and each of these analyses disfavoring these hypotheses for the MiniBooNE excess at about the 95% confidence level for the photon-like excess, and the 97% confidence level for the electron-like hypothesis. We see a little bit above the prediction in this 0 proton channel, which if I go back, you'll see is actually in this bin of relatively little signal and quite high backgrounds fluctuation in a single bin. So this is actually our least sensitive channel that we have, and so we combine this together with the N proton channel to make the statement about the overall agreement. All right, so just in the last few minutes here, this kind of leaves open the question then of, okay, so what then, right? So the MiniBooNE excess has not gone away based on MicroBooNE's data. This is still here, and so we can ask, what is it then? So there's a few options we have, right? This could be, we did very targeted selections looking for the specific kinematics of, say, radiative delta decays. So we could have a signal that has very different kinematics in, say, the photons or hadrons that would have been not selected by these first searches. Perhaps some other new physics like decays to asymmetric E+ E- pairs or boosted E+ E- pairs. Kind of coming back to that chalkboard drawing I had of other possibilities. So I think we have still quite a rich theory landscape to explore. This chart shows some of that, some potential MiniBooNE explanations and what signal topologies they correspond to. And this is an incomplete list of papers about them. The references are on a backup slide. In any case, so what was included in these searches is this array of topologies with 4 particular kinematics. And we're actually now developing the next round, which will both generalize these searches to a broader kinematic range and also start to explore some of these, so far unprobed different topologies that are just simply would be cut by our current selections. So one can also ask, what happened to the sterile neutrinos, right? So the still allowed parameter space, MiniBooNE, with this MiniBooNE interpretation. So MicroBooNE alone cannot probe this parameter space with high significance. So that is the goal of this full multi-detector program, combining all of these near-far. We'll be able to provide 5 sigma measurement or exclusion of the full LS&D allowed region using this complete set. And this is under construction now. SB&D, and again, Icarus is coming online. So this is in the near future. SB&D, being quite close to the target, will also see relatively huge flux of any kind of new particles produced in the beam relative to what MicroBooNE sees, and Icarus being larger than MicroBooNE, we'll see large statistics from the new beam. So all of this, starting with MicroBooNE, carrying on with the full SBN program, and then eventually leading into DUNE, is I think a very exciting program ahead, right? So with that, I will summarize. So for now, for MicroBooNE, we have studied these leading hypotheses for the MiniBooNE anomaly, one of the most significant anomalies out there in neutrino physics, looking in multiple different complementary search channels, and found no excesses thus far in our currently analyzed data set in either this neutral current single photon production or a new E excess hypothesis. There remains, however, a rich landscape to be studied. The MiniBooNE anomaly is still there. We have both higher statistics in MicroBooNE and a broader range of signatures that we're looking at now underway. This is a kind of standalone complementary but related analysis looking at E+ E- pairs produced in the new beam stop, but porting analyses like this to the booster, for example, will allow us to search for these kinds of boosted decay topologies. And all of this ties into an exciting future at SBN and beyond. So we will have dramatically expanded reach in the future with MicroBooNE, certainly with SBN and future LArTPCs at DUNE. But in the meantime, MicroBooNE supporting work, the extensive analysis, reconstruction, the systematics, developing all the supporting work for this will all help to build up this program. So with that, I thank you. I'll leave you with the references for all the key results here, and of course, thank my collaborators who made all this possible.